Hello everyone, welcome to this video of integrals and calculus. For this video we're going to be continuing Feynman's technique and also learning something called contour integration. And once again I took this integral from the internet, and I'll be posting the original video of how the guy solved it, but we're going to be solving it a different way using this. So the first thing that I notice when I see this integral is the ln x to the power of 4. That's going to be kind of difficult to deal with, and especially if we want to use contour integration. And the reason is because if you guys have ever done complex numbers, you might know like the complex number I, for example, that's e to the I pi, but it's not just that, it's plus like 2 pi k, where k is any integer. So there's actually infinite representations of I. And so obviously if I'm taking ln of I, that can mean either I pi, or it could mean that I have, let's say k is 1, so then I have I pi plus 2 pi. And that's technically it's a different number. So that's why the logarithm function is a multi-valued function in the complex plane, and contour integration it's part of complex analysis. You're building a contour in the complex plane, so that's why you can do logarithms, but you're gonna have to do something called branch cuts, which is a little more advanced, and we're not going to deal with that right now. So the first thing is to get rid of the ln x, and in order to do that we are going to use Feynman's technique. So let's recall, if I have some like exponential function, if I take the derivative in terms of t of this, then we're going to get x to the t times ln x, right? Just chain rule. So let's say I take the derivative again. Now I'll take the derivative of this. It's going to give me x to the t ln squared x. All it's going to do is produce another ln x. I think you guys can see where I'm going with this. If we take the derivative 4 times, so let's just say like 4, then we're going to get x to the t ln x ln x to the power of 4, which is what we have here, right? So that's all I'm going to do. So last time what we did was we actually straight up differentiated our integral, right? And we made a differential equation. You don't always have to make a differential equation. It could just be also just integrating it back and solving for c. In this case, we don't need to solve for c, because actually what I'm going to do is introduce a new function, differentiate that function to turn it into the one that we have now. So this type of Feynman's technique, it's a lot easier than the other video. So all I'm going to do is define my integral like this, because now when I take the derivative 4 times in terms of t, recall we're taking the partial derivative in terms of t, we're treating x like a constant, so this is going to be sort of untouched. We're going to x to the t ln x to the power 4. Okay, now we still have this, which I don't like, so what we're going to do is evaluate this at t is equal to 0, right? And if we do that, or actually I'm not going to write it out, but if we do that, x to the power of 0 is 1, and we just get our original. So we're going to say that this is really I, the fourth derivative of 0, I of 0. Okay, so now our mission is going to be solve this integral, I of t, and then take the derivative of what we get 4 times and then plug in t equals 0, and that will be the answer. And this we can actually use contour integration on. So how do you do contour integration? Well, the first step is to define the function that we're going to be doing in the complex plane. So f of z, so we use z in complex numbers, just convention. So z is going to be z to the power of t over z squared plus 1. Now, we need to choose which contour we're going to use. So I vaguely was talking about like ln x and the various branch cuts you need to make for ln x. Don't need to worry about that. We're going to go with the simplest contour for this, which is a semicircle contour. That is a really bad drawing. I'm so sorry. Semicircle contour, just like that. And it'll have a radius r. That's negative r. And we'll be going in the counterclockwise direction because integrals go in the counterclockwise direction. And okay, what does this even mean, right? So we're going to define our contour C. Let's call it C. So this contour is split up into two parts, really. So this is our imaginary axis. This is our real axis. You kind of need to know complex numbers in order to understand this. But if you look at the complex plane, right, y-axis is imaginary, horizontal axis is the reals, and our integral is strictly the reals. It's strictly from 0 to 1. So our integral is going to be from 0 to r, and in this case r is going to be 1, right? So this is sort of f of z, or not f of z, but like I of t, I guess. That's kind of what we're looking for right here. This is going to be the integral from negative r to 0, right, from here to here. So I just partitioned the real one into two separate ones because we're looking at 0. We're not doing negative 1 to 1, right? Of f of z dz. Okay? This one, by the way, is just the integral from 0 to r of f of z dz. Actually, I'm going to write it like this. This is better. Next, we have this thing. This is something that you guys will have not dealt with before. It's not on the real axis. It's purely like in the complex plane, and it's curving. So this is our contour. We'll call it gamma. So our entire contour C, so C is the whole thing. C is a closed contour, right? It's closed because there's no, like, sometimes you can have contours that are like open. This one is just closed. So this just means that it's closed. That's what that symbol means. C is equal to, and we partitioned it into separate parts. So there's this one, which I said was just like the integral from 0 to r of f of z dz, and then negative r to 0 of f of z dz, and then the integral gamma. Okay, so our target is pretty much going to be this one. So let's see how we deal with this. The thing is, basically, you're just picturing like a semicircle in the complex plane, right? And so this thing is actually going to like converge to a finite value if we have r is equal to 1. However, most commonly you'll use contour integration on integrals that go to infinity, and that's because if the circle's radius is infinite, this gamma thing is going to go to 0, which is going to be super easy, and I'll prove that for you guys. So don't worry, I'm not just going to just say it goes to 0. I'm going to show you why it goes to 0. But basically we want r to tend to infinity. So now if r is tending to infinity, this is really the integral from 0 to infinity, right? So I'm going to replace these with infinity, and that does not match what we have here. But don't worry about that. We're going to deal with that later. For now, we're actually going to say that I of t is equal to, no, actually, we'll keep that for now. Yeah, we'll deal with that later. But, yeah, okay. Then the last thing we need to do is consider the poles. So what are poles? Poles are basically what make the function blow up to infinity. So in our case, it's whatever's going to make the denominator equal to 0. And so if we set x squared plus 1 equal to 0, we're going to get plus or minus I. So I is here, negative I is there. Negative I is outside of our contour. So you can do a full circle too. In that case, negative I would be in there. However, I chose this semicircle contour so that we didn't have to deal with an extra pole. You don't need all the poles. One pole is suffice, so that we can use something called the residue theorem on the entire contour. So if we have a closed contour that has a pole in it, if there's no poles, the closed contour is equal to 0. And we might have an example like that in the next video where we'll have no poles in our contour. In that case, the contour will be 0. But in this case, we do. So our contour C is going to be equal to 2 pi I times the limit as Z approaches our pole I. And then you're going to do Z minus the pole I. And then we have X, or sorry, not X. Then we have f of Z. So this. And we need to evaluate this thing. And so this is really just I to the power of t over 2I. That's gonna that's gonna cancel out nicely like this. So that's gonna give me pi e to the I pi over 2t. E to the I pi over 2 is just another way of expressing I. I showed you guys that at the beginning of the video, but also it would really help if you know how to express complex numbers in their polar form. And yeah, this is going to be a pretty long video. But anyway, so now we have our contour C, but remember, we're looking for this. So that's not the answer. We're not even close to the answer just yet. Okay, now this is sort of our target for now, I guess we can say. What about this one? Well, we don't like these bounds, first of all. Don't like those at all. Well, we want to turn this somehow into our original integral. So, or not our original integral, but this one, to make our lives easier. So I'm gonna just replace f of z with what f of z actually is, which is this. And now, if we just do a little substitution here, we take z to the negative z world, which means that dz is going to the negative dz world, right? That would mean that our bounds would change to infinity to 0, but we can use this negative to flip the bounds. So we're going to get from 0 to infinity, and then we're going to have negative z to the t over, and then this is going to just be z squared plus 1, because negative 1 squared is just 1. But then we can take the negative 1 to the t outside. Right, so let's just call this I. So this is going to be equal to negative 1 to the t I. This will be I. And this we just figured out is negative 1 to the t I. And so solving I is what's going to help us solve our original integral. Now we're going to solve gamma. So the integral of gamma. Gamma is this contour, this thing. So it's really going, right, from 0 to pi. If you know the angles, right? This is a 180 angle, pi. So it's going from 0 to pi. And we have to parametrize this as well, because this is like a line integral. If you guys have not dealt with line integrals, I mean, I actually haven't. I don't like fully understand how this works. I just sort of know the methodology, I guess you could say. But yeah, it's going from 0 to pi, and we're going to say that z is going to be parametrized as r, our r over here, e to the I theta. So it's going across all of these different angles, and theta is our variable, right? Because we're going from this angle all the way to that angle. And so that's why our angle goes from 0 to pi, if that makes sense. R is just what we're multiplying by, because that's our radius. So now dz is going to be equal to, I guess, I r e to the I theta d theta. Right? That's pretty simple. So now we're going to replace all of our z's with r e to the I theta. So we'll have r to the t e to the I t theta over I to the t, r to the t, no, sorry, r to the t, e to the I, t, no, what am I doing? R squared, e to the 2I theta plus 1. And then we have I, r, e to the I theta, d theta. Perfect, okay. So now we can't like directly evaluate this integral, obviously. So we're gonna have to use something called squeeze theorem. You might have used that when we did limits. So essentially, the absolute value of gamma is gonna be less than or equal to the integral from 0 to pi of the absolute value of the inside. And this can be proven using the limit and sum definition of integrals. So I'm not going to prove it, but you can see if you just look at the definition, it makes a lot of sense. But remember, the absolute value of this is just going to be its radius. So we're going to be left with r to the t, and then we're going to have r squared plus 1, and this is also going to become r d theta. And notice how we don't have any thetas. So this is really just going to be r to the t plus 1 over r squared plus 1 times pi. And if we take the limit as r approaches infinity, well then this is just going to be equal to 0. Right? Because this grows faster. Perfect. So now that we've proven that this is equal to 0, our new expression, so here, this right here, pi e to the I pi over 2t is going to be equal to 0 plus I plus negative 1 to the power of t times I. We're going to just factor out that. Perfect. Remember what we want is I. And I'm going to rewrite negative 1 just to make this a little cleaner. E to the I pi t. There we go. And we can actually divide both sides by that. So we'll have pi e to the I pi over 2t over 1 plus e to the I pi over t. That's going to be equal to I. And now we were going to differentiate this, right? But this is kind of ugly. I'm thinking... I'm thinking if we multiply the top and bottom by e to the I negative pi over 2t, right? Right, because this will become 1, and this, okay, perfect. So this is actually just going to be then half of secant of pi t, right? No, pi over 2t, right, okay. So this is just using the definition for cosine. If you guys remember this. We covered this, I think, in a different video. But that's all I did here. So now we're going to have to differentiate this thing 4 times. Yeah, I don't really want to do that right now. So what we're going to do first is explain how I'm going to turn this into the integral from 0 to infinity, right? So let's go back. We have this. Right? Okay. But we're dealing with this one right now. So we can split this up into 2 separate integrals. Our target integral, but then also we have, sorry, what am I doing? X to the t. Like this. So all I did here was partition it from our bounds and this new bound. And the nice thing is we can turn this into our bounds. That's sort of our goal here, right? So we have I of t, And if I just say that x is going to the 1 over x world, and that means that dx is going to be going to the negative 1 over x squared dx world. So 1 over infinity, that's going to give us 0, right? So we'll have the integral from 1 to 0, and we'll use the negative to flip the bounds. So 0 to 1, and then, let's see, we will have x to the negative t over x squared plus 1, no, 1 over x squared plus 1 over x squared dx. And then if we distribute the x squared, that's when we get back our original denominator. Notice this is really just I of negative t. So what we have just calculated here, this is actually equal to that. Okay. Now if we differentiate this 4 times, so I to the 4 t plus I to the 4 negative t. So this was our target, right? We want I of t. We want I of t. Sorry, the fourth root of I evaluated at 0. So the nice thing about 0 is that negative 0 is just 0. So when I do evaluate this at 0, I can just combine these, right? So you have to differentiate this thing 4 times. Yeah, I'm not going to do that, but you guys, I'm going to leave that as an exercise to you guys, because, yeah, I'm not doing that. Okay. And then we can evaluate it at 0, so I'll just say t equals 0, and then we're going to just replace these with zeros, and then combine them, and then divide it. So this, and this will be our answer. So actually, like, it doesn't even matter what the power of this even is. You just differentiate it. Like, let's say it's ln x to the power of k, you differentiate it k times. So if anything, we just developed a general formula. Now obviously 4 was chosen so that you guys could actually do it, because you know, if there's a pattern, I'm not sure if there's a pattern, but you could maybe derive a better formula if there's a pattern, but I'm not really sure. But I do think that I just put this into Wolfram Alpha, and this is what we got, I think. So let me know if this is what you get, and stay tuned for the next video. Thank you guys so much for watching.